Hello. Today I'm going to demonstrate to you exactly how three-dimensional modeling and mobile mapping can prepare a paving site in a completely unique and innovative manner. Road projects rely on the quality and reliability of the initial data. However, in the field we face several challenges, whether it's tight deadlines, significant operational constraints, safety issues for ground crews, and very often data that is incomplete or insufficient to properly plan the work. With the arrival of reality capture tools and 3D modeling, we are now able to gain a complete understanding of the site before execution. In terms of the agenda for the presentation, we will talk about point clouds and 3D models. We will also introduce you to different reality capture tools and how they work, illustrating the various stages, whether it's data collection, processing, 3D modeling, or the analyses that are possible. We will explain the limitations of traditional methods, such as GNSS and total stations. We will also present to you the various benefits we've observed in the field, such as efficiency, safety, different costs, and the quality of decision-making as well. Finally, we'll compare the approaches to show why 3D modeling is becoming a new standard in the industry. So regarding the context of construction site reality, preparing a site relies on data that is reliable. So delays, safety issues, and lack of information complicate planning. 3D modeling, on the other hand, makes it possible to have a better view of the site before the work begins. Before going any further, let's lay out the basics. A point cloud is a set of millions of points measured in 3D. Thanks to a laser scanner, which can be true to the shape of the terrain, a structure, or a road corridor. A 3D model, on the other hand, is a digital representation of the entire project to be built. It includes various lines, embankments, slopes, levels, in short, all the elements that precisely define what needs to be built or corrected. The advantage is that these models then allow us to analyze the construction site in extremely fine detail, well before mobilizing teams or equipment on site. If we now talk about GNSS or total station surveys, these types of surveys offer good accuracy, but they are slower and a bit more expensive in the field. They require a team to be present on the roadway. As for data coverage, it is also limited with this type of equipment. Traditionally, surveys were done using GNSS or total stations, but as we mentioned, these are surveys that are a bit more localized, a bit slower, manual, and require more personnel. They often require lane closures. Data coverage remains limited to discrete points, meaning points that are directly surveyed in the field, requiring several mobilizations. These are necessary to document an entire road. For example, here we'll talk about a real-world construction site context. So if we look at the different images on the left, you can see the person surveying various points using a chain with certain distances between each point versus on the right, which is a survey done with a vehicle at highway speed if necessary, allowing you to capture point clouds and a huge amount of information from what you record using the vehicle, which is at this location. When it comes to reality capture tools, we can start by talking about drones. So drones would give you a complete aerial view. They are also particularly useful for areas that are hard to access, to quickly obtain orthophotos and digital terrain models. There are regulations behind all this which can be a bit more restrictive. However, Transport Canada has done an excellent job of democratizing the process to allow as many people as possible to use this type of device directly in the field. And the complementarity with ground surveys is also excellent. So we're talking about volumetrics, we're talking about quarries, different types of surveys like this, but also various road surveys, which are now possible thanks to the quality of the equipment we have. Another technological tool we can talk about is reality capture using SLAM, simultaneous localization and mapping. So this will be a tool that can be used for surveys that are pedestrian-based or indoors. So it can operate without the GNSS system as such, and it can effectively cover environments that are complex, like tunnels, buildings, and so on. So it's really a device that will allow you to capture data. In reality, it's for projects that might be a little smaller than those you would do with a vehicle. So they will allow you to gather a lot of information in these different environments. Next, in the reality capture tools, we're going to talk about terrestrial laser scanners. So the example we have here right now is a system that will be installed on a tripod, allowing you to perform local surveys. So starting from the tripod you have, you'll need several setups to be able to cover the entire site, which will be useful for smaller scale projects. In these cases, it's also useful for various tunnels, buildings, and overpasses. Different environments also allow us to use this type of device. And the example you see here on the screen right now, the SX12, we can use it with a pole and the data collector to take measurements. Also, various additional points can be measured in addition to the point cloud surveys that have been done. So data collection in this case is a little slower since we're set up on a tripod, but it's still very, very, very effective for data collection when we're talking about local sites. And now the last thing I wanted to talk to you about is mobile mapping. So this is really the core of today's presentation. So it's going to be here. Surveys are carried out at normal traffic speeds without impeding traffic. So we'll have a combination of LiDARs, cameras, GNSS, and inertial sensors to achieve high accuracy, as well as complete coverage of the road corridor. It's the fastest, safest, and most productive method for large-scale projects in terms of reality capture, as we've been discussing since the beginning of the presentation. For example, let's talk here about the different deliverables that can result from reality capture. So among these different deliverables, we'll have point clouds that are either raw or classified. So what we're seeing here on the screen right now is point clouds with a color applied to them. When we apply classification, that's what you see on the screen at the moment. So each type in the point cloud will have its own color. Each class, will have its own color. And then afterwards, we'll be able to select which classes we want to display or not. On our rendering, we'll also have surface models. We'll also be able to generate various longitudinal and cross profiles, deformation maps at the later stage, for example, volume calculations, excavation or pavement calculations, orthophotos that can be produced directly, and 3D panoramic views. So we can really talk here about digital twins of the construction site. So you take your construction site, you import it into your computer, so into the office, and you're able to access all the information you need. These are products that then feed into the various technical and operational decisions throughout the project you'll be working on. From the point cloud to the 3D model, there will be different steps required. This includes cleaning and aligning the data, as well as automatic classification and manual. The extraction of elements such as curbs, ditches, and structures, as we saw in the short video here, the production of a surface model of a profile, and then the integration of all this will be done in various office design software, as well as data sharing platforms. So once the data has been cleaned and classified, that's really when we start working with the data to perform various extractions and truly take the point cloud, then turn it into an actual deliverable. For the different software, whether it's in Trimble Business Center or in Trimble Connect, afterwards to facilitate visualization, communication, and sharing among the various stakeholders. So we really start from a point cloud and then move towards a 3D model that will have been created from it. When we talk about precision and data accuracy, as you can see here on the screen, this is a small example of a point cloud with different points that were surveyed with the total station directly at those locations. So you can see a bit of the difference in what we get. So yes, the precision of each of the points you see here on the screen, you can see it a little bit. The white points are going to be a little larger when we use the total station. However, you can see that between points 2 and 6, which are in the middle of the screen, we might lose different pieces of information if we take measurements every 20 meters, for example, with the total station or other methods. So that's why using mobile mapping or reality capture equipment will allow you to get a much better result in terms of data. So you will have a much larger amount of data, much more localized compared to the points you would have to survey or set with those different pieces of equipment. So if we talk about analysis and use cases, there are several things that can be done with 3D modeling. This allows you to identify areas that need correction, estimate asphalt volumes, check slopes, and compare before and after in order to reduce various unforeseen issues. So whether it's rut detection, for example, ruts, depressions, index calculations, pavement condition, PCR in English, or creating surfaces to optimize milling, this type of device can be used for all of that to achieve a better surface and truly optimize the milling on site. Calculating volumes of asphalt, excavation, or embankment is also possible. Slope analysis and drainage analysis, which are different, can also be performed using the data captured through reality capture. Comparisons before and after the various works. Marking extraction as well. So if you need to redo the existing markings, you can capture them outside beforehand, import them into your software, and then redo them directly by using GNSS systems to do the marking directly as well. And finally, there is optimal planning of the milling. So Here we see another example of pavement deformation, for instance, that we can analyze with the system or with the point cloud, excuse me, in order to get information about where the pavement might be deformed, to look at the volume, to see what should be done, to identify depressions and what we can detect. All this information comes directly from the point cloud. You have also collecting the data. We can use the drone itself. So here we see an example of an orthophoto. So that's what we're talking about. Not even from the point cloud, but it still gives you information to be able to position your chaining in different pavement widths as well. So you can position all this information directly from the data collected by the drone in the field. After that, another use we can make of the drone, but this time using LiDAR data, for example, is to create cross sections to determine drainage slopes, for example, based on what is directly on the ground. So you are able to do that. Now, regarding the quality of the sensors, with the DJI L3, for example, mounted on a Matrice 400, it will allow you to achieve the quality of the rendering we have here, as shown on the screen right now. So it can allow you to capture that information directly. Now, if we talk about pavement analysis, here we have a small photo showing an example of a traditional method for pavement analysis. So we mark the cracks, identify the defects that are present using a total station, using GPS. Then we measure, quantify, and qualify the various defects found in the field using mobile mapping. But afterwards, we'll be able to use the data that was collected with mobile mapping and various algorithms within the Trimble Business Center software. So we can automatically extract that information. We no longer need to do it, as you see here on the pavement, in that way. We just drive the vehicle and we're able to get the information we want from all of this. So we're going to look at a small example here of pavement analysis, which will be done directly from point clouds. So I really want to talk to you about this information, about what you'll be able to get. You can already see very clearly in the first image here an example of what can be done. So we can see everything that can be extracted directly from mobile mapping. So the first step we'll need to do is to classify our point cloud. What we want to do here is work only on what's on the ground. So we're going to remove, yes, the buildings, the vegetation, and so on. But as I said, we only want to keep the ground. So also remove vehicles that may have been captured during the actual survey with the mobile mapping device. After that, we simply set the analysis boundaries. So we're really telling it exactly where we want to perform the different analyses in the software once again. Then we proceed directly to the analysis. So it's the software that will allow you to perform the analysis. You will have, yes, a quality control to perform afterwards, but the majority of the information will be extracted directly from the software based on the different specifications you provide it. But the software uses the ASTM standard in order to carry out this analysis directly. So this is done according to the standard that is built into the software, the ASTM standard, which is the North American standard for all of this. Once you have defined all of that, the analysis, as we mentioned here with the standard, you can change or modify the different pavement inspection parameters directly within the software, as such, as we were saying. But by default, it's according to the standard we talked about earlier, so that afterwards you can get different results. So here you will have the results in 3D format, in CAD format. So you will have the extraction of cracks that will have been done directly from the point cloud and or the camera, always depending on what you have extracted. But you will have all that information, in CAD format, which you will be able to export afterwards. So if you want to work in MicroStation, Autodesk, or any other software, you will be able to use this information directly within the different software programs. So once you have these results in layer format, as we mentioned, in 3D format, in digital format, you can also look at the report that was generated from there. Because yes, the software will allow you to create a report, and it will give you at that point the score or grade, if you will, for the pavement inspection you conducted. You really get your grade according to the different locations, according to the different sections for this type of survey as such. So this is really the report you will get here, a PDF report or an Excel format that you can work with afterwards. And it will give you all the different types of analyses that were done, as well as the different types of defects that were found. So once again, here on the previous slide, we had a rendering or information that was a little more brief. And then as you go further down in the report, you'll be able to get much more information on each of the cracks that have been extracted, each of the fissures that have been extracted. You'll be able to access all of that information, as well as information about potholes, rutting, and donirage, which will also be extracted directly Also, all the fissures will be classified as such. So you'll have the type of fissures present in your project directly at that location. Now, if we talk about the benefits, as mentioned, the data will be very dense, so a better estimation will be possible. So the point cloud will be detailed across the entire pavement itself. The quantities will also be more accurate, and there will be fewer unexpected issues throughout your project. Safety is also increased. So whether the surveys are done from a vehicle without exposure to traffic zones, that's going to be very, very, very important as well. Just think about the information you need when you have to make requests to the ministry to be able to block roads and so on, detours, signage, and so forth. So you can use the system at highway speeds if you want directly. So as we mentioned, there's a significant reduction in risks for the different teams. We'll also gain speed and increase productivity, with data acquisition taking just a few minutes instead of hours or days, and less mobilization required. Less impact on traffic once again by using this type of technology. It also gives you solid evidence in case you ever have any claims. So the digital twin you'll have will be time-stamped. You'll have the date when the survey was done. So if you ever have any claims or anything like that, by using the digital twin, by using the point cloud with what you have, you're able to go back to position to show everyone what was there originally. We'll also have objective data to support or defend a claim. And finally, the detection of deformations, rutting, we just talked about it, but also the identification of bumps, problematic areas. Once again, this allows for better planning of milling, leveling, and paving. Thank you very much for listening today. If you have any questions, please don't hesitate to contact us.